I'm Sean Morgo. I've actually met some of you in the past. I'm a principal engineer in the Catalyst switching business unit. Uh, as they were talking about, and really, things are always changing. Obviously, we continue to evolve, the technology, state of the art. So one of my tasks is really designing and building, working directly with engineering on building the next generation of switches. So this is a wonderful representation of the next generation of switches. We actually started switching the new Catalyst 9000 with the QSFP based. The line has actually been shipping for at least a year now. But this is a brand new switch in that same family that we've introduced. So what we wanted to do was really talk about what's unique about this particular one. Now you've probably seen, the intro slide itself. The key thing to take away from this is 60 ports of 50 gig and 4 ports of 400 gig, all in a single rack unit. Of course, that we have bigger switches, we have modular switches, but this is the first to ever introduce 60 ports in just a single one rack unit pizza box. Now, what kind of things we're going to cover today? I thought I would start with what's inside of it. Like I was saying, we've actually been shipping this family, this group of switches for about a year now. So go back to kind of even why that's important, talk about, what's important about a core, what even is a core, and, and I try to bring up some, what are the common questions, particularly, for the audience, why are we doing another switch? And what's interesting about this particular switch? And the most important question of all, why should I even care? But really anchor it on this new technology, this Cisco Silicon One ASIC family. And then from there, I said 60 ports of 50 gig. Okay, it's a number, 50 gig, but how do we actually achieve 50 gig? Why is 50 gig interesting for me? Are there different options? Should I, as part of the audience, actually be looking into 50 gig and those kind of things? And all of this is really just to level set, right? And then, of course, get into the switch itself. Why this particular switch? So if you mix together those 2 points, what's new about this ASIC, what's new and happening in 50 gig, and then putting all of that together into 60 ports in a single rack unit, right? So like I said, at the end of the day, it's really about why I should care. So I'm not going to go and dig into every single detail, but really try to touch the finer points. And if you guys have any questions or you get questions from the audience, just let me know. So first and foremost, again, this is level set, right? We have a wide breadth of Catalyst switching from the access layer switching, which is really connecting to the users, right? So this tends to be copper-based, power over Ethernet, and these kind of things, spread between modular switches and fixed switches. But then you look over onto the right-hand side, the entire core portfolio, which these tend to be fiber-based, because this is now connecting all of those many different access layer switches all together into your core. And then from a campus environment where Catalyst is normally operated, connecting to service provider, connecting to the data center, and those sort of things. So again, that kind of really lends itself to why this particular switch. And then, in the last year, 2022, we started shipping this new X series, right? So that's kind of the second part you see on the top. We like to joke that the X stands for expansion. It's not that I've actually changed, the nature of access switching or core switching, but I need to, continue to increase. My access layer is increasing. We have things like Wi-Fi 6, and so bandwidth is increasing, number of users are increasing, et cetera, et cetera. That's the why should I even care part, right? Now, and I did mention the QSFP model that we've been shipping for a while. QSFP tends to be more of a very high bandwidth, 100 gig. We just recently introduced 400 gig Ethernet in this QSFP form factor. But you're like, okay, that sounds neat, but that's where I'm connecting to the data center. So how do I actually connect the data center to all of my users in the campus? But then when you think about, okay, that core then needs to connect all of these access layer switches, that tends to be in an SFP form factor, right? So then we start having a 10 gig Ethernet, 25 gig Ethernet, and again, 50 gig. So that's the new thing. That's what I'm talking about today. So like I said, let's take a quick trip down the ASIC history. And just like I started with a recap of the portfolio, I thought it was useful to talk about what is the core and does it even matter, right? Some people will put, a data center switch in their core. They'll put a service provider switch in their core. And when you're just talking speeds and feeds, that's fine. We call these like a generic core. When I start to apply specific services to it, what makes a campus unique, and particularly the types of scale. So a generic layer 3 core, honestly, it can be anything. It can even be other vendors that I will not name, but basic speeds and feeds, any box in this class should do it, right? There's even the far extreme, which is collapse core distribution. And again, we have other Catalyst 9500 switches that fit that role. So it's really about this middle one, number 2 and number 3. Of course, we've been talking a lot about software-defined access and EVPN, so we can support that as well. But the one I want to draw your attention to is this core plus edge. Okay, so it must be everything that's the basic speeds and feeds of an L3 core. But you'll probably notice there's some like rainbowy colors. What are these rainbowy things? These are things like VPN services, L2 and L3 VPN services. Very, very high route scale. So that's where the name edge comes from. So perhaps I'm connecting to my internet edge or connecting to the service provider edge. So being able to take the entire internet routing table into this box, okay? Specifically, this model does 2 million IPv4 routes. It gives you an idea. I can take 2 million routes in there. So that's kind of how we spread those across. The existing 9500 for collapse core distribution, not as high scale, not as high bandwidth. But if you want the really high scale, really high bandwidth, that's where you would use the 9500X. Okay, and then again, what we're just adding is this new model that I'm talking about today. So that kind of tells you why core. Why does core edge matter? Like I said, 2 million routes, much higher bandwidth. It's enabled by this new Silicon One family. Again, we've kind of talked about this a little bit. My service provider friends are also using this Silicon One ASIC family. It's another interesting thing for the audience, that unification of the ASICs between service provider and campus. Specifically this Q200 model, you don't have to remember all the details. What I want you to remember is that 12.8 terabits on a single system on chip, SoC, okay? Now, I know this is a technical audience. I could have just given you a bunch of fluffy slides, but I wanted to put in some cool techie slides to really reinforce that. So you already said the single system on chip ASIC, built in a 7 nanometer form factor. So that's like extremely small in nanometers, but all of that shrunk into a single chip. It is what's called a multi-slice. So if you're looking at this photograph, it's kind of a weird photograph, but you'll notice it's in 6 individual columns. So when we use these buzzwords like slices, what we mean is that each slice is an independent ASIC by itself. So I've actually multiplied 6 of those into a single package. And that's how we're able to achieve this 12.8 terabits. Other interesting things, this 256 SerDes, which that's another geeky term, but serializer, deserializer. So these are the serial channels that go from the chip to the front panel ports. Cool. What I really want to draw your attention to is this 56 gig PAM4. It's pulse amplitude modulation. Another interesting geeky thing. But it's essentially doing coarse wave division multiplexing on the serial channel, CWDM. So I'm able to get 4 times the performance off of that same single channel, right? So that's why it's magical. You're like, okay, that's just some weird words. But each one of these serial channels operating at 56 gig. So that's how we can suddenly give you such high performance, right? Other interesting things in here, it's an onboard buffer most chips have this. But in addition to that onboard buffer, it also has an external buffer called high bandwidth memory. So it's both this local low latency buffer plus very, very deep buffers, up to 8 gigabytes of high bandwidth memory. I mentioned earlier this 2 million, it says longest prefix match, so specifically like IPv4 routes from the internet, right? In addition to that, then this central exact match, so very large, these typically, just like it sounds, exact match. So these are like your MAC addresses. I need to exactly match the MAC address. Going to be your multicast routes, ARP, neighbor discovery. So if you're thinking about like centralized wireless, I know the team has a lot of wireless team come in. This device can then take all of those MAC addresses, all those ARP entries from that wireless LAN controller and terminate it on this one box. Okay? See, and I even set up my own slides. So the centralized wireless is one of those key examples. I won't belabor the point, but I thought a nice visual would help you see that. Typically, you would connect your wireless LAN controller directly to that core device. And then wireless access points use a tunneling capability called CapWAP, right? So why do I make that point? That tunnel means that it's just layer 2 until it gets here. But when it pops out of the wireless LAN controller, that's where I resolve my MAC addresses and my ARPs. So if you're doing like, you know, hundreds of thousands, if you're a university or a hospital with hundreds of thousands of wireless clients, that's one of the reasons you would choose this box, okay? And then the other one I also mentioned, you know, we have a variety of systems, but there may be a situation where I want to actually just place a very high performance switch into that internet edge role and be able to take the entire internet table, which is currently sitting around 850,000, 900,000 IPv4 routes. Okay. All right. So to really drive it home, you know, I talked about the big buffers, and in fact, I think this picture is worth 1,000 words. Okay. I'll talk about this one in a second, but I'll start here. So I talked about this like local on the chip type of memory. Every switch in the world, every ASIC in the world has this type of thing. It's really for low latency and ideally very high performance. I can like take the traffic, do my lookup and get it out as quick as possible. Minimum latency, that sort of thing. But then you have these crazy applications. They may be very bursty. You know, I've long-lived traffic. So other technologies try to use these massive, massive buffers. We believe that both are the best answer, to have the best of both worlds. So we have a 80 megabyte local and 8 gigabyte high bandwidth memory on this Q200 chip. So along with that is virtual output queuing. So I know some of the audience may have heard VOQ before, but it just like it sounds, it's to the virtual output. So it's actually an ingress buffering, but the egress is telling me, hey, you know, I have enough bandwidth to send or not to start buffering. So really to prevent these things of like head of line blocking. So I just try to give some basic examples. I could have lots of flows going to one uplink. This is quite common in the campus. I have a big uplink going to the data center. So all these flows. Or the reverse. I have this like, you know, multimedia stream coming from the data center and I need to send this out to lots of users. So that's the quality of service and these, again, high bandwidth type of applications that we're starting to see is one of the reasons for using this. All right. So that was just a quick recap. Why do I even care about the core? And
quick question, if you don't
yeah,
mind.
please.
So if you have that amount of buffer space, is that actually enough? If you have like you mentioned 60 ports of 50 gigs and 4 ports of 100 gigs,
400 even.
or 400. Okay,
Yeah.
then it makes more sense, I guess. But is that enough?
Yeah. So I could actually spend a whole tech field day talking about this topic. And that there are like opposing theories around this. A lot of times there's another terminology called buffer bloat. So there's a whole nother philosophy which says give massive buffers, but exponentially you wind up with like terabytes of buffering. And so the studies have shown that, you know, as I'm transmitting, the bottom line is this: I want to get the packet out as fast as I can. So particularly like in data center and service provider, they actually prefer the smaller buffers because I want at line rate to dequeue and minimize the latency. But But then exactly to your point, in fact, your question sort of supports my point. But then I do have applications that are just sitting there, they're lower priority, but I might need lots and lots of buffers just to hold on to them for a moment. So that's where the HBM kicks in. So it's actually the combination of these two that addresses that.
Okay, so you have some intelligence based on when you're going to use 8 gigabytes buffer memory compared to just using the 80 megabytes?
From a packet forwarding perspective, they always come into this local, and these are just acronyms. It stands for shared memory system. So all packets will always enter into this shared memory system. And then based on your QoS policy, they will then be moved to the HBM, right? So that's why I kind of drew it this way with the colors. I know it's kind of hard to read, maybe even on camera. But your voice and video, real-time traffic probably will never leave this low latency, but it's shallow, it's smaller in that sense. But then all of these, just basic file transfers or whatever, then I will temporarily stick those into the HBM.
And you supported HQoS, right?
Yes, we do support hierarchical QoS as well. Yep, 4-level HQoS.
But only on the consideration, most times buffer kicks in, correct me if I'm wrong, but you have a big pipe, let's say 400 gigs coming in, yeah? And then you have some devices that are connected with a lower bandwidth. So let's say these ports. And these are actually the points where you need the buffers most, yeah?
That's correct. It is sort of its own, scientific discussion. We could have like a QoS focus one, but you're exactly right. That's kind of the purpose of this drawing. The so-called uplink is 400 gig, and then I have a set of 10, 25, 50 gig going to the access layer. So you're exactly right, and there's a speed mismatch. It's not that he cannot possibly do 400 gig by himself, but then I need to slow it down and then transmit it.
Yeah, the misconception often people think, oh, it's a higher bandwidth port, so I need more buffer. No, it's the other way around. If you have low bandwidth ports, there you need buffer.
They're waiting. They have to sit and wait. That's right. Okay. All right. So that tells you why this Silicon One Q200. Again, we have other 9500X. We also have the modular 9600X. But let's talk about this box and particularly this idea of 50 gig SFP. And the other thing I'll call out, because it'll start like repeating itself, is this SFP 56. Remember I was talking about 56 gig PAM4? That's a clue about its signaling and how that technology enables the ability to do 50 gig. So this is a wacky, busy slide. The reason I put it here was really to drive home some key points. It's less about the copper. We could have a copper discussion, but particularly SFP versus QSFP in the fiber environment for the core. So and we talk about the 400 gig. That's a QSFP DD. So what's interesting is and why I chose this slide. What I really want you to see is the type of connectors. So as we were developing 40 gig and QSFP, which the Q in that sense is a quad, by the way, if you're curious. But it really comes from what's called a trunking cable. So in the old days, in the beginning, you would only see these on patch panels, and I would take a bunch of smaller fibers and I would just patch them together, and so it was trunking these together. Somebody realized, well, hey, why don't I just do that multiple fiber signals into a single interface, right? And that was the birth of QSFP, right? Cool. But again, we talked about campus, right? So in a data center where perhaps the next device is 1 meter away, I can just go over and connect some new cables. It's easy. That's not how it works in campus, right? Campus, the cabling is in the wall, and this building was constructed maybe 10 years ago, 20 years ago. So what you find in most campus environments is I'm actually using this older LC type cable, 2-pair LC cable, and nobody is going to pay to replace that cabling, right? But now I'm trying to enable Wi-Fi 6 and I've got more users and my boss is telling me I need to increase bandwidth. How am I going to do this, right? So that's the part I want to draw attention to, is really why in campus SFP is so important.
The good old octopus cable style, yeah. But what I learned a lot in the data center, often you have good measurements of every cable, you know the quality of the cable. In the campus, in old-fashioned office buildings, of nobody has measured that. And then, yeah, it says OM4, but if you do really measurements across your fibers, you find out, oh, the guy who did this here didn't pay a lot of attention when doing the actually connectors and so on, yeah.
That's exactly right. And like how it moves through the walls, you have strange bends in the cable, and yeah, that's absolutely true.
Even if it says, I don't know, you have a certain amount of meters, be careful with that. It really depends on the quality of the fiber and especially on the connectors that are at the end, yeah.
That's right. Absolutely. Okay, so another busy slide. What to read in here is that for the Catalyst, we've been trying to answer this. We've actually been promoting 25 gig for some time now. And the only thing to really get from this slide is this first one, reduced Capex through reuse of existing cable. So it was exactly this point. They are not going to let me rip out the cable in the wall. So how do I, as a network administrator, enable higher bandwidths on the exact same cable, right? So enter 25 gig and now 50 gig using the exact same cable, okay? So we offer a variety of these options across that Catalyst portfolio, you know, from the existing, you know, prior to the X series as well, now carrying to the X series.
I have one question for this 50G. Do you see 50G mainly as just switch to switch, or do you see that the server manufacturers are also will adopt this widely and that you see kind of switch to server connectivity also with 50G?
So we are seeing this. Typically, this ends up being a the cost, the server manufacturer cost. So and sort of this repeats itself, right? We went from 1 gigi trying to convince the server manufacturers to introduce 10 gigi. So this is happening again. That we're trying to convince them to use 25 gig and then on to 50 gig. So, in fact, this entire story, it's a great question. This is still new, right? So even just from a pure introduction to the industry, 50 gig is still very, very new. So in that sense, it will be more of a switch to switch for now. And then as the manufacturers also begin to adopt 50 gig, then you will see much more to the server.
Yeah, maybe it also depends on the longevity of the hardware, because 5-6 years ago, we were designing for 10 gigabyte networks for servers to switch. Now it's 25 with NVMe and so on, and can probably in the next 5, 6, 7 years, this is going to be the next iteration.
Yeah, I think blade centers where you have a lot of server density absolutely makes sense. Yeah.
Yep.
That.
And even it's an interesting connection. Like the different options that are out there, it says 100 meters, 30 meters, it's whether it's on a multi-mode fiber, and then you get into many kilometers over single mode fiber, that sort of thing, right? The good news is that we have options for all of those. And there's more even than on this slide. That's actually led by our transceiver module group. So it's uniform across, service provider, data center, and campus.
Is that including BiDi?
They will have a BiDi option, yes. This is anyway 2-pair, but the signaling form of BiDi, they will have a BiDi 50 gig. I almost had a slide to show the 56 gig PAM4. I didn't end up showing it, but what I opted for was a picture up in the corner just to show you how they combine those signals together to achieve 50 gig. So hopefully I made people excited about 50 gig. We could have a whole session on 50 gig. I just wanted you to know why this is going to be valuable on this switch. All right, so I intentionally kind of use these why do I care slides. And we've talked through it. So by this point, it should be pretty obvious. It is incredibly expensive to replace all of your cabling. Perhaps maybe that new building that I'm designing, I can afford to do it, but nothing that's already in the walls. And, you know, I'm going to talk about this in just a moment, but we say double the performance is in this case going from 10 gig to 50 gig is actually 5 times. You know, so it's whether, which gets me to the second one, multi-rate optics, right? This is very similar to the multi-gigabit Ethernet on copper. You were asking about the quality of the cable. And also how expensive, right? So some human being has to go out there, some poor engineer, and replace the optics. That's part of the fact, right? So what is it going to cost me to go out and replace these based on the quality of the cable? And these can operate at 25 gig and 50 gig, right? And so what I'm sort of saying about this is you could actually do it by starting at the top and just work your way down. And it depends on what the other side is speaking, right? So in this example, I only have a few core switches, so I could change those to 50 gig on this side of the cable, and then let the distribution layer continue to operate at 25 gig. And it's just going to downrate itself and operate at 25 gig. Some fine day, I now have the money, I go and get the other side. It will immediately then begin operating at 50 gig, and then you just work your way down to the access layer.
Then you will need good buffers at the layer wherever you are.
Exactly. It's all part of the process. Okay, so all of that, like I said, was to just make a big deal about the switch itself. So I now have incredibly high scale, very high buffering, and I've managed to pack 60 ports, 60 ports, into a single rack unit on this switch. You know, in fact, I almost want to back up to the drawing itself. At the end of the day, you know, one of the most important things is density, the number of ports themselves. And this is like a costing, but also like the management of the device itself. Of course, you can go up. We have this modular chassis option, the 9600. But there, you know, somewhere in between, it's like at what number must I now change to this modular chassis? So this was specifically to address that place where, you know, typically switches are 48 ports. What's very innovative here is building it in a way that can support 60 ports. So many of the things we've already talked about, 2 million routes, very deep buffers, VOQ. It says 2 levels of HQOS, it's 4 levels. Another interesting thing down here, it's kind of hidden. This has built-in hardware to support IPsec. It does have a footnote on it, and that's really just about software support, which we're going to be releasing quite soon, later this summer. But the hardware itself, of course, has to be built to support that hardware IPsec encryption. So this will be the first in the core. We already have access switches in the 9300X that does IPsec, but this will be the first core boxed to support IPsec. So in addition to very, very large number of ports, very high scale, I can now also do layer 3 encryption off of this.
Just one question. Do you have the MACsec feature also on the 400G ports?
Yes, all of these ports. And since you asked, so LAN MACsec is, the term is not actually a thing, it's just MACsec, 802.1a. But what is interesting is there's also this term WAN MACsec. It's also known as ClearTag. So you're using .1q sub interfaces, and you present this .1q VLAN header in the clear, so you can form the MACsec key exchange. But the important thing is you're doing it over the WAN. So we can do all 3 of these. We can do traditional LAN MACsec, WAN MACsec, and IPsec in hardware. Okay, it's a busy slide. I don't want to read every single point to you, but I really drive home that port density, right? So what you'll notice here is this innovative 3-row design. So again, traditionally it's 48 ports. By taking on this new 3-row design, and you'll notice there's a small space in there, that is where the motherboard, the PCB, is located. So you still have the traditional 2 cage on top. And then what we've done is we've flipped and stuck this 3rd cage on the bottom of the motherboard. So that's the new interesting in how it actually works. But with having that, then I can put 30 here, 30 there, 60, and you notice it's 10, 25, or 50 gig. And then talk about the uplinks, connecting data center, service provider. These are QSFP DD, so they can be 400. There's even a new standard for 200 gig Ethernet, and of course 140 gig, all in those same interfaces. So flexibility, very, very high density. There are other interesting things. One thing I didn't talk on the last one was this, particularly on this fixed one, is reversible airflow. So the fan trays themselves can come out. These are, they're colorized, so they're red or blue. But the point is I can just take out the fan trays and replace them, and the airflow now is in the reverse direction. So I'm going to actually show it to you guys on the screen. You can see kind of the internals and how airflow behaves. But that's another hardware innovation that we've brought to this new chassis.
So that is at the end. So many moons ago, I saw the first 48 port switch. I said, okay, this is the end. Yeah, now you have a third row. I think this is kind of, there's not much space left.
Correct, yeah. Correct. And you know, even the point I was making earlier about just the SFP form factor. So as you get into these larger, you know, it's a square versus a rectangle. So you probably will not see 3-row QSFP, but SFP does enable this 3-row design.
So and that must have also been some sort of heat dissipation issue, right, for the ports, because you're having more at the same space, so that it gets a lot hotter.
Yeah, that's a great question. There's a couple answers to this. One, I can go either way. Many people ask us, why did we choose to put the QSFP in the middle? Is exactly your question. So for thermal reasons, that the QSFP are much hotter than the SFP are. So from, you know, the air intake coming in, it's much easier if it's in the middle because it'll just naturally exhaust. We did add additional airflow, and even in between the LEDs themselves, there's more airflow. It does have some restrictions with the very, very high, like the ZR, or the ER optics. But what we've done is just limit how many are adjacent to one another if you have these very, very high power. But all the normal SR, LR are within thermal limits.
And the M2 storage down there, what's that for? Is that for storing PCAPs, or what are you doing with it?
So this system also supports the application hosting. So we also have this Intel-based x86 architecture, and there are data path from that Silicon One ASIC to the CPU for application hosting. So it's actually mostly a storage for application hosting, but you can also store, you know, iOS images and these things on it.
You could run Thousand Eyes on it, can't you?
And you can run Thousand Eyes on it. Absolutely.
I'm curious about how, there was some kind of limitation with earlier platforms on how many hardware offloaded BFD sessions you could have. Do you have full support for, do you know what the number is for a hardware BFD session?
Yeah, it's 128 sessions.
128?
Yeah.
Okay.
That still exists.
Yeah.
It's mainly if you have a bidirectional forwarding detection, you know, I'm generating hellos between you and I, and then how many of those can I do in a session? So that's still true. Yeah.
This is still generated by CPU, the hello packets?
So we can do both. That's what's interesting. Now we're deep into the ASIC itself. It has built-in ARC processors, very similar to ARM. But it's a localized CPU that can generate things like BFD, OAM. But the software itself, iOS XE software, can also generate a BFD session.
I'm coming from the security side, and this was often what stuff is generated still by the CPU so that we can somehow overwhelm this device. Yeah, so it's good that you can do that in ASIC as well.
Absolutely.
How loud is it when you turn it on?
Okay. This is not a fanless switch. This is actually very high performance. I don't know the decibels offhand. We do have less than 80 decibel limits. So I know it's less than 80, but I don't know the exact number. But it's loud. I mean, it's normal, standard, like data center core class loudness.
So I can heat my office with that as well?
It's very interesting. The Q200 ASIC, because of how massive it is and how much is being, I just very briefly talked about 7 nanometer. Just imagine all of that pressed into 7 nanometer form. So it gets exceedingly hot. But when you do have a chance to look at it, you'll notice it's a very large heat sink. And so just like the questions with the optics, like we have done special airflow design to keep it within limits, but it's hot. It's hot.
So it probably can't run with the plastic lid on.
It probably cannot run with this plastic lid. It looks really cool. I've actually had customers ask me that, like, does it ship this way? I'm like, it's sitting in a rack. No, it doesn't ship this way. It comes with a nice hard metal case.
For long, at least.
Yeah, not for very long.
You mentioned SDA and BGP EVPN. Are there any roles in SDA that they cannot perform?
So that's actually an interesting question that you chose. It is designed at that core and edge layer. It is intentionally designed to be more of a border node, a control plane node. Then you get into what is an edge node, right? So can it perform VXLAN encapsulation, all of these things? Absolutely. And as a border, I need to do that. I'm the end of the encapsulation. But as an edge node, I'm also doing things like 802.1x, traditionally access layer functions. So like we do not support 802.1x on this because it's a core box, right? We can, by the way, we can, but today we do not do that. What it does do is more of a distribution layer. So if you have this like policy extended node, I'm not doing .1x, but I need to advertise the MAC addresses and have that Anycast gateway. That is fully supported. So it's more of the like true edge stuff that's not on there.
So traditionally we've seen the CATs in the campus layer and Nexus for the DC, but do you see this going in the DC as well for a while Nexus maybe catches up with some of these features, sort of feature parity?
Yeah, and that's why we emphasize this core plus edge. It's a good question. And I always say there's a natural overlap, right? There's an unnatural overlap. There's a point at which you've extended something into a completely different role and it doesn't fit very well. And then there's a healthy overlap, right? But talking about that core plus edge, so another word is like a data center interconnect, right? So it's at some point I need the campus to connect to the data center, right? And we also do BGP EVPN, for example. So yes, it can be that data center interconnect. You would probably still have a Nexus box in your data center, but something needs to connect these two, and that would be this box. I have some eye chart type of things, really just to show like cable counts. All this stuff is available online, so you do not have to memorize this. It's just to reiterate kind of the reasons I would choose this are to have this very dense native. I don't need a breakout cable. You mentioned breakout cables. I can also then use breakout cables on the QSFP ports if you actually want more. But it is built for that very high density native ports. We talked about this in number, but I thought it might be interesting for the audience to see this in a scale comparison format. So it's showing the 9500X and the 9500. So like this row, for example, longest prefix match, 2 million routes versus 256,000 routes. So that is when I'm again connecting to the internet and those types of things. And I mentioned that wireless, centralized wireless case. In both of these examples, we also can change the scale of the ASIC. So that's why you're seeing a default and a maximum. What we have is the table is like available for whatever I want to program in it. And then I can reserve pieces of that table, right? And then I can change that reservation, right? So it's It's a take from one, give to another. So for example, I have a wireless design. I can actually change it from 128,000 to 256,000 by taking some of these other, perhaps I'm not using MPLS. So I could reduce the MPLS and give all that entry to wireless and so on.
So one question that catch my eye. So most of the numbers, of course, are better at Silicon One, but the security ACLs have gone down. What lead into that decision, or why was it kind of in the design that you?
Yeah,
abandoned?
this deserves a full discussion by itself. The short answer is we do a lot of our security group ACLs, where there's a big push in SD access and these things, to bring those services to the edge, and then that interconnect layer tends to have less services. So that's the primary reason.
So kind
again,
of the design consideration is more security ACLs at the edge, in the distribution layer not so much, yeah?
That is a wonderful segue to what is almost my last slide. These both exist at the same time, okay? Don't think of these as a replacement. Think of them as two different tools in the same toolbox. And then to your point, it's kind of hidden in here, but if you're thinking of more features and particularly things like access control list, but not about the scale of forwarding, you should be thinking about the 9500. If you are thinking more about very, very high scale and performance, then you should be thinking the 9500X. Yeah, it's a great point. So in summation, we actually have been shipping that QSFP 9500X, and we are just now introducing this SFP-based 60L4D, starting in this 17.10.1 software version. And if anyone's interested, we have a online Catalyst 9000 ebook. If you're watching it, you can actually scan the QR code. It is available, it's free, and it will tell you all the information, including the X series in this third edition of the book.